Hi, my name is Patakituro Sitakun, and I'll be discussing about Lab 1, which is constant velocity. So, what is the purpose of the lab? The purpose of the lab is to observe how an object moves over time when it is ideally in constant velocity. Additionally, we will observe the differences between experimentation results and the computational model's predicted trajectories. But first, let's talk about some physics principles. Newton's second law. Newton's second law states that the rate of change in momentum is equal to the vectorial sum of forces on the body. Basically, if we added up all the forces acting on something, the change in the momentum would be equal to that with respect to direction and magnitude. This explanation can be easily summed up by the equation on the slides. Specifically for this lab, the object is unaffected by external forces, meaning that it is in constant velocity. Let's derive this. We started with the same equation as before. First, we just multiply time to both sizes and replace momentum with its definition. Then, change in velocity is replaced by final minus initial velocity, and after some rearrangements, we get to the bottom equation, which is the velocity update formula. This models how velocity would change given the sum of forces and how long the forces were interacting with the object. With that out of the way, let's go to the experiment. First, a video of the cart gliding along the track will be recorded. Then, we upload that recorded video into Tracker and track the cart's position. This will help us accurately determine how the cart moves with respect to time. Third, we graph the experimentation results in Excel. After that, we create the computational model with GlowScript. Then, we graph the computational results in Excel. And finally, we compare the two results. Now, let's go over the conditions and setup of the experiment. The object we will be tracking is a cart, which is placed on a track. Once the video starts, the cart will be pushed from one side of the track to the other with enough speed. We will only use a small portion of the cart's movement when tracking. Now let's take a look at the video. Now let's look at the cart's movement. The red dots you will see on the screen are what is being tracked, and I chose to track the front of the cart since it's easy to consistently determine where the front of the cart is. Now, let's calculate the average velocity of the cart from our experiment, so that we can model its movement in the GlowScript. We can use v equals distance over time to calculate the velocity. I use the start and ending points of the cart to reduce errors in velocity calculation. And the result we get is around 0.75 meters per second. Next, let's look at the GlowScript. The ball's original position is the origin, and the ball's velocity is what we just calculated, which is around 0.75. Since the tracker measures in intervals of thirds of a second, that is what we use for delta t. Since the tracking took place until 0.567 seconds, that is what we set as the while loops condition. Since we assume the cart is moving at constant velocity, the net force is assumed to be 0. And what was derived from the position update formula. Then we add that net force times delta t over mass to the ball's current velocity. And since the force is 0, velocity should not change at all. And then after that, we update the position by adding the ball's velocity multiplied by delta t. And after that, the ball's position is updated, we update the time, and repeat this process until time is more than or equal to 0.567 seconds. The experiment and simulation results match quite nicely. The orange points, which is the simulation, and the blue points, which are the experiment. They line up to form a straight line, indicating that there were minimal external forces involved in the experiment, and that the velocity was basically constant. Though the points don't line up perfectly, and why could that be the case? Some possible sources of errors are external forces, such as friction and air resistance, and additionally there may be some tracking errors, which may cause the position to differ slightly between the experiment and computational model. So let's ask some what-if questions related. What if the axes were to be flipped? For example, what if the positive x and negative x axes interchanged? Well, nothing would change except for the slope becoming negative if the axes were to switch. The line would appear to be sloping downwards since time would be moving from right to left in the graph. Finally, what do the results mean? Is the net force 0? The answer is still no, even though the experimentation says otherwise. The reason for the experimentation results comparing well with the computational model is because of the short time frame of the video, reducing the effects of any change in velocity. Addition to that, there's also minimal friction from the track and minimal air resistance, which could cause the velocity to change. Though these forces are still acting on the cart, and if we were to record a longer video, the cart would definitely slow down. Next, how many forces were added together? Gravity and normal forces acting vertically cancel out, and as I said earlier, air resistance and friction are still being added to the net force. However, it's so small that it's negligible. Thank you so much for going through my Lab 1 video.